In this lesson we're going to look at how the concentration of the reactants affects the rate of reaction, again in the context of collision theory. So thinking about this idea of concentration, we're going to look at two situations. First of all, that of a solution where the reacting particles are dissolved in a solvent, for example such as water, and in the case of a gas, where changes in concentration can be interpreted as changes in pressure. Okay, so first of all, thinking about the solution, okay, we've got the reacting particles and they're dissolved in water, for example, and again they're moving around within the water at a whole range of velocities and different directions with different energies. But what we've said in the previous lesson still holds for the situation. There can only be a reaction if there is a collision between the reacting particles. So if we want to increase the probability or the chances of a collision, then one of the ways we can do that is increase the concentration of the reacting particles. For example, okay, so in this case we've got a low concentration. I'll write conc for concentration, and in this case we've increased the concentration. We've got a higher concentration. As a result of that, there's more chance of a collision between particles, and therefore there's more chance that one of those collisions will be successful, resulting in a reaction between the particles. So by increasing the concentration of the particles dissolved in solution, we can increase the rate of reaction. Similarly with a gas, rather than talking about the concentration, we're talking about the pressure. So really it's the same thing. By increasing the pressure of a gas, that's to say we're increasing the number of particles within a unit volume, and that's effectively the same as increasing the concentration of the particles in the gas. Okay, so here we've got the gases at a lower pressure. There are fewer particles per unit volume. By increasing the pressure, higher pressure, then we increase the probability again of a collision between the gas particles, and therefore we increase the reaction rate between those particles. So let's just summarize that. By increasing the concentration of the particles in solution, okay, or by increasing the pressure of the gas, we're going to increase the number of collisions that are taking place, and will effectively increase the reaction rate between the reacting particles. Okay, so let's just take a practical example to demonstrate this principle. As we've been doing with the last three lessons, we're going to keep with the same reactants. We're going to look at the reaction between zinc and dilute hydrochloric acid. Okay, so we've got identical pieces of zinc at the same temperature. Keep the temperature constant, no catalyst is being used, but what we're going to change in this case is the concentration of the two solutions. Okay, so this is a dilute hydrochloric acid solution. This is a hydrochloric acid solution with a larger concentration. Let's just say, for sake of argument, this has got a concentration of 0.5 moles, and this one has a concentration of 2 moles. Just for the sake of argument, okay, and okay, so what we've done is we've changed the concentration of hydrogen ions, and it is the hydrogen ions that will react with the zinc. So if you like, there are 4 times as many hydrogen ions dissolved in this solution, they're both of equal volume, as there are dissolved in this solution, because the concentration 2m is 4 times greater than the concentration of this one, 0.5 m. Okay, and we remember that in the reaction with zinc and hydrochloric acid, you're going to get plus hydrogen gas, and it is the hydrogen gas that is being released here and filling up the syringe and forcing the piston to move to the right. And so, as you'd expect in the more concentrated solution, what you will see is that the piston in this case will move faster than in this case, because there's a greater concentration of hydrochloric acid, which means there is a greater chance of collisions, which means there's going to be a greater rate of reaction in this case than in this case. So this reaction will go faster. Okay, so one thing we'd like to look at now is how the concentration affects the way a reaction progresses. Now this would apply, for example, in this particular case where you're reacting a metal with an acid. Okay, how would we expect the rate of reaction to change with time? Okay, so this graph shows a typical rate of reaction curve. Let's just think about what's happening in terms of concentration. So first of all, initially you'll notice that the curve is very steep here. That means it's got a high rate of reaction, and the rate of reaction is high because there's a very high concentration of reacting particles. But what happens as those particles start to react? Well, they will react to form the products. What does that mean? Well, it means that the concentration of the reacting particles will gradually become less and less. So when we reach this part of the curve here, we've got a lower concentration of reacting particles now. That means that there is less probability of a collision between those particles, which means that there are fewer collisions, which means that the rate of reaction here will be less, and as that reaction continues, this concentration will still get less. So the curve is steep here, it's less steep here, and finally when we're getting here to this point, the curve is nearly horizontal because nearly all of the reacting particles have been used up. The concentration at this point is very low, and eventually the curve will become horizontal when all of the reacting particles have been used up and the reaction effectively stops. Okay, so just to summarize then, during this phase of the reaction we've got a high concentration of reactants, and this results in a high reaction rate and therefore a steep curve, while during this phase of the reaction, the end phase of the reaction, we've got a low concentration of reactants, much lower concentration, which results in a low reaction rate and results in a shallow curve.